Next, I have for you an example that is a two-sided test regarding hypothesis testing about a population parameter. 20 years ago, 57% of parents of children in high school felt that it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 368 of 900 parents of children in high school felt that it was a serious problem that high school students were not being taught enough math and science in the recent survey. Is this enough information to say that parents feel differently today about the issue than they did 20 years ago? And we're going to use alpha equals 0.01 as the level of significance. Before we calculate the sample parameter, what we're supposed to be checking is the claimed parameter from the null hypothesis in condition 2 here. So we are plugging in 0.57 when we convert that to a decimal. The sample size was 900. And multiply by 1 minus 0.57 as well. 220.59 is greater than or equal to 10. That wants rounding. Now, we are not told what the population size is, but 900, what that would be 5% of, is 18,000. And that's far smaller than the population of parents with children in high school. So definitely 900 is less than or equal to the population size. The sample, are we told that it is random? I am not seeing it, but let's say that it can be reasonably assumed to be random. Hopefully the survey was conducted properly. Okay. So the null hypothesis, the parameter, you always have equal in the null hypothesis, and equal to that 57%. Then in the alternate, still about P, and a not equal because we're asking if it's not equal. You're comparing against the same number, 0.57. So what is the test statistic? We need to figure out what 368 divided by 900 is, first of all. And this formula we used before. What I would be doing is replacing p hat with the answer we just found. We are subtracting the 0.57. And in our denominator, what we are dividing by, we needed P, as in P naught, the claimed population proportion, times 1 minus that, and divided by the size of the sample, which was the 900. We're supposed to round that to 2 places. So that is coming out to be negative 9.76 after the rounding. Yep. I meant to type negative 9.76, but it must have had a tolerance that it would accept how far off we could be. So, determine the critical value. Let's see here. We are testing at the 0.1 level of significance. Because this is two-tailed for a two-tailed test with a 0.01 level of significance, plus or minus 2.575. Okay, it did say to round to two places. So let's see if that is the only thing going on here. Okay, now we're good. So let's take a look at the board again. We calculated a t-value of negative 9.75, and we're getting a critical z-value of 2.58. Alpha is being split across the two sides, 0.01. And so what we're asking is, do we have something extreme enough to put us in the bottom 0.005? Think of that as an area, or if you put that as a percent, a 0.5%, or the top 0.5%. And the cutoff score on the left side was the negative 2.58. Not that this is meant to be to scale, but we're way left of that. We are in the critical region with that z-score of negative 9.75. So what that's going to lead us to do is reject the null hypothesis. We are in the critical region. Our probability would be smaller than 0.01. There is significant evidence, statistically significant evidence, sufficient evidence that students today feel differently than they did 20 years ago. Okay. One more thing here. If we took twice what we have in normal CDF, we standardized, and that was negative, so I'm going to use a negative 10 to the 99 for our lower bound because it's headed towards negative infinity. Take that answer that I had as the last thing in the screen here. We've standardized, so 0 and 1 here. And it's not that it is 0, but it is so small it's indetectable to the calculator from 0. That means that if the null hypothesis were true, it's very improbable that we would have come up with the sample that we did and the sample parameter that we found, p hat.